Welcome to the fourth and hopefully final lecture video for the second class time series of lecture videos. I'll try to get through on the material in this in a brief amount of time that we're all still hanging in there with it by the time we finish. Allylic halides are excellent substrates for SN2 reactions. So recall the molecular orbital description of the SN2 reaction from first semester organic chemistry, CHM233. Here we have sodium hydroxide attacking methyl iodide. We've got our nucleophile, our hydroxide, taking a lone pair of electrons, using it to form a bond to carbon, kicking out an iodide anion, which gets together with the sodium cation, and we form methanol, right? Crude molecular orbital diagram description of this process, you might look at hydroxide as having a filled sigma oxygen hydrogen molecular orbital, and then there are three non-bonding pairs of electrons on oxygen, and our non-bonding pairs of electrons always go between the bonding molecular orbitals and the anti-bonding molecular orbitals. In this case we have an anti-bonding oxygen-hydrogen molecular orbital. So the highest occupied molecular orbital is one of those non-bonding pairs of electrons on the oxygen. A crude molecular orbital diagram for methyl iodide is below, right? We've got three sigma carbon-hydrogen molecular orbitals, and of course if we have three sigma bonding carbon-hydrogen molecular orbitals, we've got three anti-bonding sigma star CH molecular orbitals. Then we have a sigma carbon iodine molecular orbital that's bonding, and then of course we've got a sigma star antibonding carbon iodine molecular orbital, and then we have three non-bonding pairs on iodine. Well, we know that our methyl iodide has an electropositive carbon. It's going to want to accept electrons from a nucleophile, so it will be taking those electrons into the lowest unoccupied molecular orbital, and that will be the antibonding carbon iodine molecular orbital. So of course, carbon sp2 and 1s combinations are much lower in energy than our carbon it's an sp3 hybridized carbon and methyl iodide. So these are carbon sp3 1s combinations versus a carbon sp3 and iodine is using a 5p atomic orbital, so that's a higher energy combination, right? An sp3 and a 5p versus an sp3 and a 1s, and that's why our lowest unoccupied molecular orbital is the sigma star carbon iodine molecular orbital. And here we have a visualization of, our hydroxide with a pair of electrons pushing that electron density into the back lobe on carbon of this sigma star carbon iodine molecular orbital, which has a node between the carbon and the iodine. And of course, the effect that this will have, putting electron density in that sigma star carbon iodine molecular orbital, is to break the carbon iodine bond, right? And we are forming an oxygen carbon bond in this transition state. So how does this all tie into allylic systems? That's a good question, and of course the answer is with some interesting molecular orbital cartoons. Let's consider the SN2 reaction rates of 3-chloro-1 propene and 1-chloro propane with sodium iodide and acetone. So here we have allyl chloride, here we have our 1-chloropropane, and we're reacting with sodium iodide and a nice polar aprotic solvent. For our allyl chloride with iodide at 50 degrees C and acetone forming allyl iodide and chloride, our relative rate is 73 versus an SN2 reaction of iodide with 1-chloropropane at same temperature, 50 degrees C and acetone, to form 1-iodopropane and chloride. We set that at a relative rate of 1. So what this is saying is, allyl chloride is 73 times faster in terms of its reaction with iodide than 1-chloropropane. So there's something that lowers the activation energy in the transition state of our nucleophile attacking this carbon on allyl chloride. There's something special about that neighboring pi bond that lowers that activation energy versus 1-chloropropane, which is saturated and has no pi bond. Let's see if we can suss it out by looking at pictures of the transition state in terms of what they would look like with the molecular orbitals drawn out. Here we have our 1-chloropropane, saturated, no neighboring pi bond, right? Here we have iodide donating an electron pair into our, chlorine, carbon, antibonding sigma star molecular orbital. Versus what? Versus having this neighboring pi bond, right? Same sort of transition state. But what's special here? What's special here is, yes, we've got p orbitals on these neighboring carbons, and guess what? They're filled with electrons, right? And so that pushes electron density through an interesting phenomenon called hyperconjugation into what? Into this transition state of iodide pumping electron density into the sigma star carbon chlorine molecular orbital. So if you have more electron density in that transition state, guess what? It helps push the chloride out faster, right? Because we're souping it up. We're, making it turbocharged with additional electron density from that neighboring pi bond that can overlap, right, perfectly with these phased orbitals and really push that electron density in and help ease that chloride out. So what do I say in words about this? I say the pi carbon-carbon bond of the 3-chloro-1-propene can donate some additional electron density into the sigma star carbon-chlorine molecular orbital as the reaction transpires. That is, as the non-bonding pair of electrons on iodide donates into the sigma star carbon-chlorine molecular orbital, and that lowers the transition state energy, so it makes it go faster, which is why we record a rate that's 73 times faster than the reaction of iodide with 1-chloropropane. So hopefully that's an interesting way of visualizing this sort of SN2 reaction with our neighboring allyl group, and why that's special compared to saturated hydrocarbons. So last thought for this video, and we'll get this class done in a series of 4 videos, is allyl organometallic reagents. In terms of their formation, we could actually deprotonate our propene, right, our allylic carbon, because the pK of propene is 40, whereas the pK of a saturated hydrocarbon is about 50. So the equilibrium constant for this reaction is 10 to the, conjugate acid pKa minus the pKa of the acid, which ends up being 10 to the 10th. This is much greater than 1, so we definitely favor the right side, and here we're forming an allyl lithium and butane. Another way we might represent allyl lithium instead of a covalent bond between carbon and lithium, which we know to be polarized, such that the more electronegative atom carbon dominates in terms of possessing the electrons in that bond, is drawing it out in an ionic sense. Here we've got an allyl anion and a lithium formal cation. The truth is somewhere in between this. Of course, another way we could do this is we could simply, throw allyl bromide or any other allylic halogen in with magnesium and generate, in this case, an allyl magnesium bromide reagent. We can buy this too, of course, if we need to use something like this, to react with other things in lab. So that does it for this 4th video. Good luck with the video questions, and I'll see you in class.